Hey guys, this is Mr. Robeson again with statistics. We are going to look at what's called a Chi-Squared goodness of fit test today. So it's a new test. It's like a hypothesis test, but it involves a different kind of distribution. All right, and this one might be a little bit longer than some of the other videos because I'm combining some things here. But the Chi-Squared distribution, instead of looking like a normal distribution, looks like this distribution right here. All right, and this distribution, as you can see, is skewed to the right, and it's always shaped like that. So the distribution that we're looking at, that we're working with for chi-squared, is skewed to the right. All right. This distribution comes up when we are working with more than one categorical variables, and we're seeing if the proportions match for all the different variables. All right. So we'll have multiple categories, and we'll see if the proportions are going to match. So the way we calculate our chi-squared value is this little formula right here. So we can use the formula. We're also going to have a shortcut, but what this formula says is we have some sort of observed value. This is our sample value right here. And we're going to subtract from it what's called our expected value, which we're going to have to calculate. Then we're going to square it, and then we divide by the expected. That's our way of making a proportion out of it, is by dividing by the expected. All right, and we do this for every single one of our values, then we add them all up. Remember, this symbol is to add. That's our summation symbol. And when we add them all up, that gives us what's called our chi-squared value. All right, then what we do is we draw our little curve here if we want to. We label where our chi-squared value is, and we find the area to the right of that. So that's basically our p-value from before. All right, the way we find that area is, well, instead of serving normal CDF, now we're going to use the Chi-Squared Cdf, which is on the same menu, but it's number 8. And when we get there, it's going to ask for our lower bound. This is where we put what we got for chi-squared. Our upper bound, we just put something big like 1,000. And our degrees of freedom is the number of categories we have minus 1. So degrees of freedom is a new thing. We're not going to worry too much about what it means. It's just for our intents and purposes, it's categories minus 1. All right, and then we just press enter a few times, and the calculator will give us our p-value, and then we do our conclusions just like before. All right, so how does a chi-squared goodness of fit test work, or what we call a GOF, goodness of fit? So it answers the question, does a distribution of a categorical variable with 2 or more categories fit the expected results? So we take one sample, we break it up into categories, and we ask, do those categories fit some result that we think they should fit? Like, in other words, are they uniformly distributed, or are they evenly distributed? In other words, is there the same amount in each category, or roughly the same amount in each one of those categories? So like we could do this with M&Ms. Do we expect to get the same amount of each color of M&M? So color would be our variable there. If we're rolling a die repeatedly, we can get the numbers 1 through 6. Do we get the same amount for each one? All right, so that's when the test is used. So in our first box here, we're going to state our null hypothesis and our alternative hypothesis. The null is always that it's, or for us anyway, is always going to be that it's evenly distributed or uniformly distributed. The alternative is always going to be that it's not evenly distributed. And that's all we need to state here. We don't need to list any statistics or anything like that. If we do want to write down our alpha value, that's fine. All right, we go over to checking our conditions. This is called a chi-squared goodness of fit test. We need a random sample just like before. We need to check independence just like before, 10 times our sample size, and should be less than the population size. All right, and this is the new one. So instead of normal, because it's not a normal distribution anymore, we get that our expected counts, all the expected values should be greater than or equal to 5. The way we're going to get this is just n divided by the number of categories. It's not that hard. N divided by the number of categories. All right, when we get to our calculator, there's 2 ways we can do this test. It's built in on that stat menu. So we go to stat, and then we go over to tests, and it's built in as a chi-squared GOF test. Or we can do it by hand, which hopefully we'll do it at least once by hand here, where we calculate our chi-squared test statistic here, and then we use the Chi-Squared Cdf to find the value. And then just like before, if p is low, reject the ho. And then our second sentence is, do we have evidence or not for the alternative hypothesis? All right, so here is our example. So do M&Ms from a random bag of M&Ms, every bag of M&Ms is random, by the way, show evidence that M&Ms do not follow a uniform distribution. All right, so our null hypothesis is that M&Ms are uniformly distributed. That means there should be the same amount of each color, or roughly the same amount of each color. And our alternative hypothesis will be that M&Ms are not uniformly distributed. All right, and we'll use an alpha value of 0.05 like usual. So now what we need to do is, well, we open up our bag of M&Ms, and here's our bag of M&Ms over here. And those are going to be our observed values. So that's what we observed from the bag. So it looks like we have 12 orange. So over here for orange, we've got 12. For blue, it looks like we've got 9. So we observed 9. For red, that looks like 10 to me. For green, a lot of green. We've got 15 greens there. Brown, we just have 5. And yellow, we just have 5. So those are our observed values. Now, if we add these up, 5 plus 10 is 15. Plus another 5 is 20, plus 15 is 35, plus 12 is 47, plus 9 is 51. Or not 51, 47 plus 9 is 56. There we go. So 56 is our total. That means our expected value for each one is 56 divided by, let's see, we have 1, 2, 3, 4, 5, 6 categories. So 56 divided by 6, which I believe is about 9.3. And that's going to be the same for each one of them. We would expect 9.3 of each of these colors. I know you're probably thinking, how do we get 0.3 of an M&M? It doesn't matter. Doesn't matter. All right, our plan. So over here, we're going to do our Chi-Squared goodness of fit test. First, we need a random sample. All right, it was from a random bag of M&Ms, so we're good there. Check. Next, our expected values are 9.3. So 9.3 is greater than or equal to 5. Check. And we had a sample size of 56. 56 times 10 is 560. Surely there are more than 560 all M&Ms out there. And this is what gives us our independence. All right, so now to do. So we could calculate this by hand if we wanted to. The way we would do that, we would, for each observed value, say the first one here is 5. We do 5 minus 9.3 squared divided by our expected 9.3. Plus the next one is 10 minus 9.3 squared over 9.3. Plus, and then we just keep doing this. And I'm just going to put dot, dot, dot. Plus all the way to the last one here, we'll have 9 minus 9.3 squared over 9.3. And now we have to type all this into the calculator. Ooh, that's where it gets to be not so fast anymore. All right. So we pull up our calculator. The first one is 5 minus 9.3, close those parentheses, squared, divided by 9.3, enter. 1.988. Plus, and now we're going to do the same thing for the next guy here. So we've got 10 in parentheses minus 9.3, close parentheses, squared, divided by 9.3. Enter. 0.05. 0.05. Not very much there. Plus, and then we're going to do the same thing here. Well, that's another 5, so that's going to give us this same number again, 1.988. By the way, each of these numbers is called a contribution to the chi-squared value. So this is how much this guy contributes. This is how much this one contributes. This is how much the yellow contributes. For green, the contribution is going to be, parentheses, 15 minus 9.3, parentheses, squared, divided by 9.3, 3.49, plus for orange, looks like we got a 12 there, so I'm going to cheat here a second, enter, And I'm just going to change the 15 to a 12. A little bit faster, I think. It's 0.78 plus, and then the last one here, we have 9. This one's probably going to be our smallest because it's closest to 9.3. Second enter. I'm going to change this to a 9. So 9, and then delete the 2, and there we go. 0.009. I'm just going to round that to 0.01. All right, and now we want to add all these up. So if we add those up, so 1.988 plus 0.05 plus 1.988 plus 3.49 plus 0.78 plus 0.01 gives us a chi-squared value of 8.3. All right, now our degrees of freedom, we had 6 categories, so that means our degrees of freedom here is 6 minus 1 is 5. And now we could go calculate the chi-squared. It's the same menu as the normal menu, so we do second distribution. There's our chi-squared. We use that to get our p-value. The lower is going to be this 8.3 we calculated. The upper is going to be, you can use 1,000 basically every time here. Your degrees of freedom is 5. And if we press enter here, we get 0.14. .14. So our conclusion is, well, 0.14 is greater than 0.05, so we do not reject our HO. We do not reject the null hypothesis. We do not have evidence. Have significant evidence that M&Ms are, and we're doing for our alternative here, not uniformly distributed. All right, now I bet you're thinking, that took a long time. Is there a shorter way we could do that? There is a shorter way we could do that. So let's take a look at the shorter way we could do this. So the much faster way is to put your data into lists. So here's our observed data. Here's our expected values. All right, let's show us how to do that. So the way we put stuff into lists, so it says right here stat, then number 1, and then type in the numbers. So we press stat, and then number 1, and then we're typing in the numbers. So I've already got them typed in here. If you need to clear them out, you can. It's real easy. You just highlight the top and just press clear, and then press enter. See, they're gone. So now type them again. 5, enter, 10, enter, 5, enter, 15, enter, 12, enter, and 9, enter. And I already typed in our expected counts. They're right there. So once you have all those typed in, we're going to go over to stats and tests. Stats, over to tests. We're going to go down to chi-squared goodness of fit. It's actually easier to go up because it's a long ways down, but there it is, option D, chi-squared goodness of fit test. So we choose that. All right, our observed, we put in L1. Our expected, we put in L2. That's usually the easiest way to do that, is just always put the observed in L1, the expected in L2. We need to put in our degrees of freedom, which is 5. We had 6 categories, minus 1 is 5. And we go down to calculate here, and we press enter. And there's our chi-squared, 8.28, which is the 8.3 we got before. Right, that would round to 8.3. This is actually a little bit more accurate. And we get 0.14 as our p-value, which is the same thing we got on the other page. And here's our contributions. If we just arrow over right now, those should be just about the same. Like we had 1.988, 2.0. It's just a matter of rounding differences. All right, so there is all of our contributions. And we would write down our chi-squared, our p, and our degrees of freedom. All right, so we got one more example here. We'll try and make this, we'll do this one on the calculator. And let's switch to a different color here. Purple, sure, why not? All right, so we're looking at Skittles. So let's take a look at the Skittles. We want to know, are they evenly or uniformly distributed? So our null hypothesis here is that Skittles are evenly or uniformly distributed. Our alternative hypothesis will be that they are not. So Skittles are not evenly distributed. All right, and the only other thing I need to put here is my alpha is 0.05. Next, do we have a random sample? All right, we sure do. Any bag of Skittles, they're kind of randomly placed in there, so that works. Our expected counts. Well, we need to add up all of our Skittles, so we might as well start organizing our Skittles here. So let's see, we've got green, yellow, orange, red, and we can argue over this if you want, but those are supposed to be purple. A lot of people say that those are brown. All right, and this will give us our observed. So it looks like we've got 12 green, 9 yellow, 15 orange, 13 red, and 8 purple. And if we add those up, so this is going to be our observed. If we add those up, well, I'm going to grab my calculator because I'm being lazy today. So let's see, we've got 12 plus 9 plus 15 plus 13 plus 8. 57, and we're dividing that by 5 colors. So 57 divided by 5 gives us 11.4. So our n here is 57. Our number of categories is 5, and we got 11.4. So each one of them is going to have 11.4 for our expected counts. So our expected is 11.4, which is greater than 5. So that checks out. For independence, 10 times the 57, the number of Skittles in the bag is 570, and surely that is less than all Skittles. All right, so that checks out. Now we do our Chi-Squared goodness of fit test. I'm going to do it on the calculator this time. So to do it on the calculator, I need to put these data into lists. So I go to Stat, Edit. All right, I need to clear out the M&M stuff. So I go up to highlight the list name, and I press Clear, and then Enter. And then I type in the numbers. 12, Enter. 9, Enter. 15, Enter. 13, Enter. 8, Enter. And now I go over to the next list. I also need to clear this guy out. So highlight the list name, press Clear, press Enter, and then we're going to type in 11.4 for all of them. 11.4, Enter. 11.4, Enter. 11.4, Enter. 11.4, Enter. And I just need to do it until they're the same length here. 11.4, Enter. And now they're the same length. So now I go over to Stat. Go over to my test. I'm going to arrow up to get to it. There it is, option D, Chi-Squared goodness of fit test. My observed were in L1. My expected are in L2. My K was 5, so that means my degrees of freedom is 4. And we calculate. So our DF was 4 here. And we get that Chi-Squared equals, let's see, 2.9, and our p-value is 0.57. All right, so we can get high p-values here, but they shouldn't be bigger than 1. So look for the E on the end if they're bigger than 1. So our p-value, 0.57, is much bigger than 0.05. So we do not reject the null hypothesis. We do not reject the HO. That means Skittles looks like they are fairly evenly distributed. So we do not have evidence. Not have significant evidence that Skittles are not uniformly distributed. So we do not have evidence that they are not uniformly or evenly. We used evenly here, didn't we? Evenly distributed. All right. So that is how we do a Chi-Squared goodness of fit test. Again, if we wanted to check the contribution for each of these numbers, the first thing we'd have to do here is just start arrowing over. If we do anything else first, it won't let us arrow over and we have to do it again. But there's the contribution for each of those separate colors. and there's purple at the end there. All right. And that is it for chi-squared. Sorry this one was a little bit longer, but that is it.